Okay, so we've kind of skipped ahead here to chapter 15, stuff like that. So these are going to be dealing with spectroscopy, specifically UV vis spectroscopy, which is and then infrared spectroscopy at the end, which is used to identify functional groups. So if you look at the, and this is black and white, so it's hard to see, but if you look at the range of, of different electromagnetic radiation, stuff like that. So it's characterized by the length of the wavelength, so peak to peak, stuff like that. So the longer the wavelength, okay, the less energy is associated with this. And so if you have really short wavelengths, so the gamma rays, alpha rays, you're at very, very high energies. If you're at very long wavelengths, so AM radio is like 100 meters from peak to peak, something like that. FM is maybe a meter, something like that. So these are very low energy. Stuff like that. So stuff like that. But for UV vis spectroscopy, right? So we're in the visible range, stuff like that. So from red to purple, and then the ultraviolet range, and stuff like that. And so what spectroscopy really is how light interacts with a molecule, stuff like that. So does the substance absorb the light, and if it does, then what does that mean? Stuff like that. So for UV spectroscopy, typically there's two different ways you can think about this. There's transmittance, which is just the percentage of light that goes through, or more specifically with UV vis is absorbance, is saying how much light gets absorbed from the sample. So if you know how much it gets absorbed, then you can back calculate how much material you have in there. That's typically what it is. And different samples are going to absorb at different wavelengths of light. They're going to be slightly different, so that they have their own character. Fingerprints of not only where, what wavelength they absorb, but also how much they absorb. Okay, so typically how this is done is you have a light source, and it's gone. You go through a little slit to sort of have a very narrow light, and then you send it through some sort of prism to separate out the wavelengths of light, and then you can get very specific, moving this exit slit, so that you can get very specific wavelengths of light going into your sample here. You know how much light goes into your sample, and then you have a detector on the other side, so you know how much you can see how much goes out, so like that. So you know how much you put in, you know how much you got out, and so therefore the difference is how much your sample absorbed. And the way that this works is that you have wavelength going from right to left, stuff like that, and so at the various wavelengths you're going to see how much absorbance. So down here there's no absorbance of light, so the photons just go right through, but if at very specific wavelengths your sampler is going to absorb, and the higher this is, the more absorbance it is. And we typically look at, we're really interested at the peaks here, so this peak and this peak of the absorption band, and they're going to be different for every molecule. Okay. Now, one nice thing about this is that you can correlate how much absorptions you have with concentration. So this is the Beer-Lambert law. So absorption, how much the light gets absorbed is equal to some constant, something like that. So this, I usually call it the extinction coefficient. It's also called the molar absorptivity for the sample. Every molecule has their own your own version of E, or its own extinction coefficient. Some poor grad student had to look at this, to calculate this, do the experiments, and then they put in a big book, or look online or something like that. So it's absorb, so some sort of constant times the path length. So this is how much sample you go through. So if it's going through twice as, if you have, it's typically 1 centimeter, something like that. But if you send it through 2 centimeters, right, it's going to absorb twice as much. You're going to have twice as much material for that light to go through. So you have to take that into account. If it's half as much, right, you're only going to absorb half as much. So you take that into account. Usually this is 1 centimeter, but it doesn't have to be. And then the last one's just your concentration. It's typically in molar, but depending on how you have the units, doesn't matter. Stuff like that. So the absorption is going to be dimensionless. Stuff like that. So your extinction coefficient here is going to have to take into account these stuff like that. So the fact that it's centimeters per molar. Stuff like that. So okay, so here's a typical problem, right? So with that, so calculate the molar absorptivity, so the extinction coefficient. If a sample absorbs at 0.78, okay, the concentration of your sample is that. 0.6 times 10 to the minus 5 molar, and the length of the sample travels as 1 centimeter. Make sure you have the units. Okay, so it's going to be A equals your coefficient times the path length of light times concentration. Okay, so we know what the absorbance is. So 0.78. Okay, you know what? This is what you're looking for. It's 1 centimeter, and then it's 0.6 times 10 to the minus 5 molar. Okay, it's just a very basic, right? So this is going to be, so you divide both sides by this, right? So it's going to be 0.78 divided by 1, I guess centimeters times 0.6 times 10 to the minus 5 molar, right? And so if you do that calculation, it ends up being 130,000 per centimeter per molar. Okay, so this is just the constant. Typically with these problems, I'm going to give you this formula. You don't need to use it, right? So so I'm going to give you 3 of these values. You got to figure out the 4th, right? So if you know what the absorbance is, you know what I can give you what the extinction coefficient is. I can give you what the path length is. You may have to calculate concentration. But notice that one thing that's not in here, the wavelength isn't in here. That doesn't matter, okay? Because what you do is the absorbance at this depends on the wavelength of here, but you don't have to put that into the calculation. So if I said absorbance at 350 nanometers, right? That 350 wouldn't come into play in this equation. Okay, so don't put it in there. That's a common mistake. It doesn't come into play. Okay. And so usually what we do is we say, okay, what we're looking for is this lambda max. So that's the sort of the local maximum wavelength, right? So here you kind of go down here and you say, okay, yeah, it's right in there, which is 224 nanometers. Okay, so that's really where we're interested. So some molecules may have a couple of humps or whatever it is, and they'll have different wavelengths. But the max is where the local maximum for that. Okay, and it turns out, and so what's happening is the way you have this is the HOMO is the highest occupied molecular orbital, and the LUMO is the lowest unoccupied molecular orbital. And so what's happening is you're taking an electron and you're putting it up into this, putting it up here, and this gap here, okay, is going to correspond to perfectly the wavelength, the energy of that photon. Okay, so with that, so it would be, you have a so if this gap is I don't know, so with that specific energy, you go to your chart and figure out what wavelength that is. Okay, so if this is a little bit higher, right? So with that, if this gap is higher, you're going to need a higher energy photon, right? So if you want to go from here to here, right, you're going to need a higher energy photon, so it's going to absorb further down. So if this is less, right, you don't need nearly as high of energy of photon in order to go from here to here. Okay, and so that's what we're absorbing. We're absorbing those photons that correspond to that gap. Okay, and so what you're doing here is, right, you put your photon in and you pop one of those electrons up into here, from the HOMO up to the LUMO. Okay, and this is typically this is a pi to pi star. Okay, the pi electrons are going to be the lower energy one, or it's going to be easier to do these. Okay, because the sigmas down here, sigma stars up here. And stuff like that, and so it's typically a pi to pi star transition. So with that, so this gap corresponds to the energy of that photon there. And it turns out the longer the stretch of conjugation, so double single, double single, double single, double single, right? So that the longer the wavelength that you end up absorbing, right? So that what's happening is this, as you extend out the conjugation, you get more double single, this gap shrinks, so it doesn't have to absorb as high wavelength light, right? So ethene or ethylene, so that absorbs at 160, so it's a very high energy wavelength. But if you put this in conjugation, right, so double single double, right, it can absorb at a much lower wavelength. Okay, it doesn't need nearly as much. And same thing here, you have double single double. Okay, so the trend, I don't need you to know these numbers, but what I want you to know is that as you extend out the length of the conjugation, the wavelength that absorbs goes up, so it's a lower energy, right? So here in beta carotene, right, you've got this really long extended conjugation system, okay? So all these double singles all the way right here, and so that this absorbs at such a long wavelength, okay, so low energy, that it, in fact, it's in the red to orange. And so beta carotene, right, it's in carrots, which is one of the things that makes carrots orange. So like that, sort of reddy orange. So, okay. So now lone pairs can also absorb, okay, but the thing about them is that the homo-LUMO gap is much lower. Okay, so if you compare this, which is just carbon-carbon double bond, it has to go from this pi to pi star, which is a much longer wavelength. However, if you compare it to acetone, these lone pairs here and here, right, they're actually further up in energy, and so this gap is much lower, right? So this is a much bigger gap, so this has to get a much shorter or higher energy photon to be able to go here to here, right? It's a much higher, hill to jump, or here it's a much smaller hill, and stuff like that, and so it can absorb at lower energy. So this one does it 280, while this one does it 160. Okay, and this is what's called an N to pi star. So the N is where the lone pairs are, N to pi star. So transition. Okay. So infrared spectroscopy. So UV spectroscopy is typically used for looking for concentrations, right? So the concentrations and looking at extended pi systems and stuff like that. But IR spectroscopy is probably a little bit more can be quite a bit more useful because it's looking at functional groups. And so here you're looking at a slightly lower energy range down here in the infrared than the UV vis, stuff like that. So, and what we're looking at is the vibrational modes of the molecule. Okay, and so you can get these functional groups, right? They can stretch up and down, or they can, the CHs, right, they can wiggle back and forth, and you can get these sort of asymmetrical stretches and in-plane bending, and you get all these sorts of crazy stuff like that. And these stretches, okay, these different stretching modes, okay, they correspond to that vibration corresponds to a frequency of light. So the best way that I can think about this is if you have a merry-go-round, okay, so like that, if you just sort of randomly hit that merry-go-round, right, it's not going to speed up. But if you time your push correctly, right, to correspond to the speed of that merry-go-round, you can go and make it go faster and faster and faster, right? You can't just hit it randomly. You have to hit it with that speed. Stuff like that. Same thing here. You have to hit it at the right, the photon at the right frequency of this wiggle in order for you to be able to absorb. Okay. Now this is a historical quirk. Okay, stuff like that. So here, this is one of the few where the baseline, so it's read as in transmittance, not absorption. Okay, and so what it means is that up here, this is sort of the baseline, which means nearly all the light is going through this part of the spectrum. Like all of these photons are going through, and the peaks actually go down. Okay, because they're absorbing the light. Okay, the light can't go through, so there's no transmittance. There's very little transmittance here, right? There's only 40% compared to here where there's over 90%. Okay, so the peaks go down. Okay, they're like the stalactites. Okay, and so like here's a peak, like here's a peak here, peaks here, peaks there. That's how so this is the baseline. There. So this is one of the weird ones where you start at the top and then go down. Okay. Now, typically what's happening, these things are given in wave numbers, okay, in reciprocal centimeters. So it goes from 500 to 4,500. Okay. The reason why we do that is that they're just easier numbers to deal with, but all they are is just the inverse of the wavelength. Okay. Stuff like that. So 1 over the wavelength. And so instead of dealing with a bunch of decimals, right, you deal with larger, like hundreds and thousands, which is just easier to contemplate. Okay, so that's what's going on here. Okay, so what we do is we say, okay, so different types of bonds. Okay, so like this is a classic one. This CO stretch, right? So this has a characteristic of being right around 1700. Okay, so this stretch here corresponds to this peak here. Okay, so different bonds are going to absorb at different wave numbers. Okay, and so what you're going to do is you're going to get a list like this. Now, for my tests, you're gonna want to. I'm gonna give this to you so you don't have to memorize it. Okay. However, not every professor does this, and on things like the ACS final, the GRE, the MCAT, DAT, things like that, they aren't going to give you this. So it's good to at least get familiar with these things. Okay, I'm going to give you some hints in a minute on how to at least some characteristics for this stuff. Okay, and so what you do is you say, okay. Like if I give you a molecule like this, where would you expect these things to absorb? Okay, so here you've got a carbon-carbon double bond here, right? So you look on this list and you say, oh, hey, there's an alkene, right? So this is going to absorb somewhere between 1620 and 1680. Okay, so you just look at this list, and it's going to be somewhere around in there. Okay, here you got a CO bond, but it's part of an ester. Okay, so different COs are going to do it slightly different areas. Okay, so ketones and aldehydes are going to absorb at a slightly different wavelength than esters. So you have to know what this functional group is. Okay, so the esters this is going to be at 1730 to 1750. Okay, here it's a CO bond. Okay, so CO bond. So this is going to be somewhere between 1050 and 1150, somewhere around in there. Okay, and here it's just going to be a regular CH stretch, and so. Here it's not part of an alkene or alkyne or aldehyde or something like that, so it's probably going to be in this 2800 to 3000 region, stuff like that. So you just sort of see, you got to list out what functional groups are there, and you sort of match it up. Okay. Now there are some fingerprint regions. Okay, so from pretty much 2500 on, you're dealing with something. So this region here is going to be something bonded to a hydrogen. So OH, CH, NH, SH, things like that. They're going to be in this region. Okay? In this region here, from 2000 to 2500, you're dealing with double bonds. Oh, excuse me, triple bonds. Okay? So things like alkynes. Okay? Cyanides, things like that. So from 2000 to 2500, you're dealing with triple bonds. From 1500 to 2000, okay, so this is 2500, above 2500. So this is from 2000 to 2500, right? You're dealing with triple bonds. From 1500 to 2000, you're dealing with double bonds. Okay, so you're dealing with C double bond, alkenes. The C double bond to O's. That's going to pop up, things like that, right? So and then from about 1000 to 1500, you're dealing with single bonds. Okay, so these are going to be carbon-carbon single bonds, right? So CN bonds, CO bonds, things like that. Now CH bonds are going to be down here, okay, because that's something bond to H. And then here, these are sort of like bending modes, stuff like that. The aromatics are down here. Okay, so you sort of think like, these are some bending modes here, but this is single bonds, double bonds, triple bonds, things bonded to H. Okay, so if you don't want to think about all of these things, memorize that list. You can at least look at these fingerprint regions. Okay. Okay, so just for some characteristic peaks here, so the C double bond O peaks, stuff like that. So these are very, very classic, sort of right around 1700. If they give you a little spectrum, it's really hard to tell where they are, but you know at least that there's at 1700. I'm going to give you the specific numbers, stuff like that, but recognize that these are going to be very characteristic. They're going to be slightly shifted depending on what kind of functional group that C double bond O is part of. Okay, but it's a very characteristic peak. Right, so with that. So now, one of the things that happens is if this thing, right, so here's a ketone, all right, so with that, so it's right around 1720 or 1721, so with that specifically. But if it's in conjugation, right, so we have a double, single, double, so it's in conjugation with an alkene, what that's going to do is that's actually going to shift that peak about 30 to 40 wave numbers to a lower number. Okay, doesn't matter if it's a ketone or an aldehyde or an ester or whatever it is going to shift that peak about 30 to 40 down, right? So instead of being at 1721, it's shifting down to 1690, right? So it's shifted it down about 30. So be aware of that. Okay. So another characteristic peak are these OH and NH peaks. Okay, so they're right around, right there. It's something bonded to H. Okay, so it's going to be north of 2500, and they're typically typically above, 3000, except for the carboxylic acid OH, which is a little bit a lower number. But the thing that you can figure out from the OH is that an OH is typically this broad peak here, okay, which is not great because if your sample's wet, because you're going to have that in there, okay. But if you see this big broad peak, what's happening is you can pick that out quickly as that's an OH peak. Okay, so big broad peak. Because if you have an NH peak, it's going to be more typical looking in that it's going to be like this. So for cyclohexylamine, it's gonna look like this. Okay, so this is the NH peak. Okay. Now another one is the CH peaks. So these bending things right below 1000. You can get these. You can tell if it's cis or trans, things like that. The big one is going to be the aromatics, right? So you can tell if it's monosubstituted, so ortho, if they're next to each other, right? Meta or para. These things are pretty characteristic. Okay, so if it has both the 700 and 750, right, you know it's just monosubstituted. But if it just has the 750, you know that it's ortho. Okay, so one of these things, we'll talk about this in a minute. You have to be aware of what's there and what's not there. Okay, so like that. And so same thing here, right? So 780, 880, right? It'd be meta. If it was 830, it'd be para. Okay. Okay, so how do we do the structural elucidation? Okay, so what we do is we say, okay, I'm going to give you these peaks. Okay, I'm going to give you the spectrum comes out, and you say, okay, this is going to be you have a sample, you know it's either this or this. You take an IR. This is the spectrum. This is the characteristic peaks that you get. What is it? Which one is it? Okay, and so this 11 or 2150. Okay, so this one is, you sort of look at this and hey, they're right. So that it's probably this is probably the alkyne peak. Okay, 2900. Okay, so that's this is probably the this is probably just the regular CH. So the alkane CH stretch. Okay, so with that, so well they both have an alkyne, right? So with that, so how do you tell the difference? Well, think about what peaks would be here, right? So we have the regular CH and CC, although CC isn't on this regular alkene or alkane one on here. This one would also have a the alkyne peak, okay? But this one would also have, right, there's a hydrogen here, and this one comes up on this list right here, okay? So you would also have a CH peak coming off of an alkyne, okay? So this would be right around 3300, okay? Here you would still have those CH peaks and the CC carbon, the alkane peaks, okay? You would also have the alkyne peaks right here, but you wouldn't have this, okay? And so what that means is that this spectrum goes with this. Because in order for it to be this one, okay, you would have to have this peak as well. We don't have that. Okay, so you have to think about what's there. If it's not listed, there's a reason. Okay, this one corresponds with this. Okay, if we had the molecule correspond to this, we'd have to have this peak. We'd have to have a 3300 peak as well. Okay, so you have to think about what's there and what's not there. And it's not always easy. Okay. Okay, so how would you figure out if this reaction took place? Okay, and so what you would do is you say, okay, let's predict what peaks would be here. Well, there's always a CC and CH peaks, right? It's for alkane. Okay, and so, but then we would also have the CO peak, okay, going from here to here. We'd also have that. We also have that bond, and we also have the OH bond here. Okay, so we would have these two, we would have these characteristic peaks. Now over here, what would have? Yeah, well, we always have the CC alkane, okay, and the CH peaks, okay. But now we have the alkene peaks, okay, as well as these hydrogens that are coming off of that alkene, right? Alkene, right? So like that. So you would have these as well, okay? So what's going to happen is you're going to lose these, okay, and you're going to gain these as you watch. If you were to take samples as this reaction goes along, you're going to start losing these peaks, okay? Although you do end up, actually it's more this one here because you make water, okay, and that would keep this peak here. So really you'd lose the CO peak, okay, but you'd gain the carbon-carbon double bond and the CH off of an alkene peak. You'd gain these peaks coming in, okay? So that's what you have to do. You have to think about, you know, the differences between this molecule and this molecule. These would, as this goes away, these peaks, that peak would slowly disappear. It would slowly become less and less because there's less molecule, you know, less or fewer molecules in order to be able to make that go away. But as this builds up, you're going to start seeing these peaks, you know, get bigger and bigger, right? So with that, so this peak here, so you would start here, but then it would go like here, and then eventually to the baseline. Here, what would happen is it would start at baseline, and then it would go there. These, you know, it would start going here. So this one it would go this way, and this one it would start growing in. So like that. So as time went along. Okay. So for this one, okay. So here you're doing this is diazomethane. Okay. If we're just going to look at these guys here, you could also probably see the peaks from the diazomethane. But if you just look at these two, right? So they're both going to have, right? So they both have carbon-carbon and CH bonds, right? So for this methyl, okay. But they would both have CC's, CH bonds, CO, right? But here you're going from a carboxylic acid, right, to an ester, okay. And it turns out these are going to be slightly different, okay. So these are going to be different. They could be different, okay. But then you would also lose, you know, they're both going to have CO peaks, okay, CO, okay, but this one is going to have, this one's going to have an OH and this one won't, okay. So, you know, this is going to, these peaks are going to shift, okay. So this one's going to shift from here to here. So as this goes away, right, this is going to build in, and then you're also going to hopefully lose the OH peak. So these are going to lose, right. These are going to gain, right? You may get a slight difference in the CO, but that's what you need to think about. So, okay, good luck.